Hi everybody, and welcome to my latest video. Today we're going to be looking at mass spectrometry and some of the basics of how that works and how we can identify the molecular ion peak and use that in our spectral analysis. So first, a little bit about mass spectrometry. So the process of mass spectrometry involves taking a molecule, or rather a large amount of the molecule, in a gaseous form and ionizing it. Okay, we ionize it by bombarding it with a high energy stream of charged particles, either electrons or cations usually. And when it does that, the molecule itself can become ionized, and it can also smash up into a million little teeny tiny fragments. How those fragments are formed is kind of unique to each molecule, so we can identify the structure of different isomers based on the fragments that are formed. The molecular ion is really useful because that can tell us the molar mass of that compound. So we take our molecule and it becomes charged by simply knocking an electron off it. And then we break up into fragments. Okay, so mass spectra look deceptively simple. They have a range of peaks, and each of those peaks corresponds to the mass of a charged fragment of the molecule. So usually the highest mass value, that's the peak that's furthest to the right, is the molar mass, or is rather the molecular ion, which corresponds to the molar mass. And in general, the tallest peaks represent the most stable or most commonly formed fragments. So they can be a really useful thing. So the tallest peak in the spectrum is called the base peak, while the fragment with the highest mass, which is the one that's found furthest to the right on the spectrum, is the molecular ion. So those are two terms that you need to be aware of. So we can identify what the compound is by looking at the position of the peaks. So what is the mass of the different fragments, and what is the difference in mass between different fragments, because the difference in mass implies a loss of different size fragments. Okay, the most important ion, however, is the molecular ion. And the molecular ion is the peak with the highest mass to charge ratio. That's what M to Z stands for. It's mass to charge ratio. So 90% of, or more than 90% of all the particles will have a charge of just +1. So the mass to charge ratio is the same as the mass of that fragment. So the molecular ion has the highest mass to charge ratio, and it is almost always the molar mass. Now, sometimes that molecular ion peak can be very small. So that's the only risk with looking for the molecular ion. Sometimes it can be very small, and sometimes you can see sort of little shadow peaks on the right of that molecular ion peak, and those are due to isotopes of carbon and hydrogen. And I'll talk more about those later. So the size of the molecular ion peak and any isotope patterns and whether or not the mass is an odd or even number can tell us about some of the atoms that might be present in the molecule. So the first thing is virtually all molar masses are even numbers, unless there is an odd number of nitrogen atoms in the molecule, in which case it will have an odd numbered molar mass. So if you see a molecule that has an odd numbered molar mass, the first thing that should be jumping out at you is there must be a nitrogen in this molecule. If there's a nitrogen, it must be an amine or an amide. So here's an example. This particular peak, this particular spectrum, you'll see has its molar mass peak or molecular ion peak at 45, which is an odd number, and that corresponds to the molar mass of the ethyl amine. Here's one. The molar mass molecular ion peak is 73, indicating a molar mass of 73 for this compound, which is indicative of this primary amine. butyl amine in this case. Here's one with an amide. Again, the molecular ion peak here is at 73. Again, it's an odd number. It's a completely different structure to the previous one. It is a completely different fragmentation pattern, but it has the same molar mass. It is an odd number, and that is the big indicator that a nitrogen is present. Now, this one is a great example of what I was talking about. You can see there's a little peak down there at 74. And sometimes that can be a bit confusing trying to figure out which one is the molecular ion peak. And if there is a cluster of peaks around that highest mass to charge ratio, generally you would be looking for the largest of those peaks to represent the molecular ion. What you get is, because there are a small amount of isotopes or small proportion of compounds which contain carbon-13, carbon-14, deuterium, tritium, etc. isotopes, they can lead to a very small amount of fragments at a higher, or molecular ion fragments at a higher molar mass. So that's what those little shadows relate to. Okay, here's another one. Down here you can see the molecular ion peak at a mass to charge ratio of 87, which again indicates the presence of an amine or an amide. In this case, I would think that it was an amine based on some fragmentation patterns and things. Okay, now the other really useful thing that we can get from the molar mass, or from the molecular ion peak I should say, is whether or not we have any haloalkanes or halogens present. This can be really useful. Halogens contain, particularly chlorine and bromine, contain isotopes, or exist as isotopes I should say. So chlorine exists as two isotopes with a mass of 35 and a mass of 37. Bromine also exists as a pair of isotopes, one at a mass of 79 and one at a mass of 81. Normally with isotopes, you end up with one isotope which is really common and the other ones which are virtually insignificant. But with the halogens, the isotopes are equally significant. So in the case of bromine, the two isotopes are present in roughly 50% each, which means that if you take 1,000,000 bromine atoms, half of them would be present as bromine 79 and half of them would be present as bromine 81. Because the mass spectrometer identifies the mass of the fragments, and we're dealing with probably millions of molecules, because if you take even a tiny amount of sample and you vaporize it, you're going to get millions and millions of atoms in there, then half of them will be present as bromine 79 and half of them will be present as bromine 81. So you end up with two peaks that are the same height and two mass units apart. And when you've lost a bromine, you lose that 79 to 81 fragment. That still sounds a little bit confusing, so let's have a look and see what it actually looks like. Okay, so with our bromoethane, the first thing, of course, is because the molar mass of bromine is quite large, you're going to end up with molecular ion peaks that are generally over 100. If you've got bromine present, it's unlikely, unless it's bromomethane, that you're going to have a molecular ion peak at less than 100. But you see how we have this pair of peaks at around about 110, 108 to 110, I think they are, that are virtually identical in terms of height. You can see another pair down there at about 72 to 74, 92 to 94. And that pair of peaks that are equal height and two mass units apart is a dead giveaway for the presence of bromine. As soon as you see that, you need to be looking at it and going, aha, there's a bromine in my molecule. Okay, so there's your molar mass of 110, your peaks. Here we're getting a loss of 81 and 79. Okay, here's another example of it. Down there you see at 122 and 124, you've got that dead giveaway. You've also got another pair at 107 and 109, very, very small. So that indicates the loss of a methyl group. Now don't worry, I haven't talked about fragmentation yet, but I will. So we'll get on to that. But that would indicate that both this molecule has a bromine atom in it and that it has a methyl group. With chloroalkanes, you get a similar kind of pattern. But in the case of chlorine, the two isotopes are present at 75% and 25% relative abundances. So 75% of all the chlorine is present as chlorine 35, and 25% of the chlorine is present as chlorine 37. What that means is that one isotope will be present at 3 times the rate of the other isotope. So you will always end up with a pair of peaks, again 2 units apart, but the one on the left with the slightly lower mass will be 3 times as high as the one on the right with the slightly lower mass. Okay, and again you'll see that sort of fragmentation. So here we can see an example with chloroethane, and you can see here at it's about 64 and 66, there is that pattern of 2 peaks, 2 mass units apart at a 3:1 ratio. Okay, so there's 66. You've got 3:1 ratio. Take off the chlorine, and there you get the mass of 29, which is indicative of your ethyl group, which is left. Okay, so what that is telling you is when you're looking at the mass spectrum, the first thing you want to look for is what is the molecular ion? Is there nitrogen present? Is there chlorine present? Is there bromine present? Once you've answered those questions, then you are 90% of the way to identifying your molecule. You can then later down the track use the fragmentation patterns to try and identify what else might be present within your molecule. And that's something we will look at in another video.